to our PCS seminar. And it's a great pleasure to actually introduce Hosung Seo, who is an assistant professor at Aju University in Korea. So Hosung he first got his bachelor's year at the Seoul National University and then moved to the US, initially to Northwestern University and then to the University of Texas at Austin, where he got his PhD in 2013. And then post that, he was a research fellow in Julia Ghali's group the whole time, first at University of California in Davis, then University of Chicago, and then affiliated also with the Argonne National Lab. And from 2017 onwards, he's an assistant professor at Aju University. And his main research interest is computational quantum materials, where he works on several DFT kind of applications. And I hope we'll hear some of these new aspects here in first principles theory of quantum defects in solid state quantum technologies. And with that, I would like to welcome Hosung. So the floor is yours.
Yeah, thank you, Cesar. Thank you for the introduction. And I'd like to thank Dr. Arago, who is not here yet, I think, for inviting me and then giving me this opportunity. And I would like to thank all of the audiences here for joining us. Well, I first of all, I hope all of you stays well and healthy in this pandemic area, which is crazy, but yeah. So in this talk, I like to talk about some basic ideas of the research topic that I'm working on. I'm not trying to give you like all the details of the calculations and like theoretical methods, but probably I like to focus on giving you the basic idea or basic story behind this research area. So this is my outline of my talk. So first, like probably for about 20 minutes, I'm trying to give you some introduction to solid state quantum information with focus on hardware kind of point of view. And then I also discuss about some basic applications from information processing to nanoscale quantum sensing using these solid state quantum bit systems. And then in the second part of my talk, I like to give you some idea about the research work which is going on in my research group. So the first topic would be the searching of new kind of spin defects, which could be a kind of good candidate for qubit in heterogeneous semiconductor system, in material systems. And then in the second part of the talk, this second part will be in general the open quantum system research. But we are working on spin defect dynamics of quantum spins in the solid state environment. So I like to talk about issues in that research. And then please interrupt me anytime if you have any questions during the talk. Let me start with a general introductory remark. So we all know that we're now living in the so-called silicon age, which is built on silicon technology. And then those silicon or semiconductor industry or technology is built based on understanding of quantum physics. But now people are all talking about now this silicon technology is now reaching its limit. And then many people are looking into different directions and then about what comes next and what will be the next generation technology. And then one of that sort of future directions is so-called quantum technologies. And then, sorry, the interesting thing is that now, like many of these tech giants, such as Google, IBM, Intel, they're also investing on on this quantum technologies. To be more specific, the quantum technology is basically technology and science based on quantum principles, but focusing on quantum coherence and quantum entanglement. Of course, silicon technology is also using quantum mechanics, but they are not using the unique quantum properties of quantum, right, which is coherence and entanglement. But the quantum technology try to build powerful devices based on this coherence and entanglement. The applications will now the application include communication here, communications, computation, and simulation, and quantum sensing and metrologies. These are 4 main branches in quantum technologies. To realize these quantum technologies, we need basically 2 things, right? We need software and we need hardware. Software, I mean like quantum protocols or quantum algorithms, which is about how to perform, your quantum operations. But in this talk, I like to focus more on hardware side. To realize these quantum technologies, you need to have a physical system, quantum devices, right? So, and then the fundamental unit for this quantum technology, quantum devices is called quantum bit. In very simple terms, this is the explanation of quantum bit. So if you think about classical bit, you like such as transistor, it operates with a 2 bit, so 0 or 1. But if you have a quantum system, you can have also classical information as a upstate or downstate, but you can also make a superposition state of these 2 up and down states. So this is sort of coherence, right? Quantum coherence. Or if you have 2 different quantum bits, you can make an entanglement, which is not available in the classical situation at all. So this is basic idea of quantum bits, the very basic idea of quantum bit. But in real life, the quantum bit doesn't look like just Bloch sphere or 1 spin. Quantum bit looks like this. So traditionally, people have developed these coherent quantum systems using photons, single photons, basically, or trapped ions, which are ions trapped in the vacuum using electromagnetic waves, or superconducting circuit, Josephson junction. These are sort of well-developed technologies available these days. But very recently, people are now, because due to the development of this semiconductor technologies, now people can realize these coherent single quantum systems in the solid state environment, which is amazing. Because usually, if you think about solid state system, it's a dirty system, right? It's dirty and it's very heterogeneous, and you don't see any like quantum effects. But now it becomes possible to implement this coherent quantum systems in the solid state environment. Let me then briefly talk about the basic idea of these platforms in the following slide. So if you have a physical system and then you try to claim this physical system as qubit, right? Then you need to satisfy these 5 basic criteria, which is known as VNCB criteria in the literature. First of all, it's a physical system, so you have to have a well-characterized and scalable physical system in experiment. And then to be a qubit, you need to know basically experimentally. You need to figure out how to initialize your quantum state into a known, for example, ground state, right? For example, here I have n physical system, and I'm pretending that I know how to initialize or how to make all of these states to be a ground state. Then you need to know how to operate a unitary transformation on these qubits. I mean, in theory, it's a simple. You just apply unitary matrix, right? It's just matrix operation, but you need to know how to do it experimentally with a high fidelity. And at the end, after you finished your quantum manipulation, you have a qubit state, right? But then you need to know how to read out the final state of your quantum system experimentally. Of course, it's a quantum system, so none of quantum system is isolated, right? All the quantum system in real life is basically open quantum system, which means that it always interact with some environmental degrees of freedom, and then this interaction with the environment cause so-called decoherence. If you start with a pure quantum system, because of this decoherence, your pure quantum system becomes completely mixed state at the end. This is not what we want. We want to be able to do all of this quantum operation within this decoherence time. This is a great challenge in the solid state quantum information literature. Okay, so once you satisfy all of these 5 criteria, then you can claim your system is now basically operating as a physical qubit, not logical qubit, but physical qubit. Okay, so then how do you sort of implement such single quantum system in the solid state, right? Satisfying all of these 5 criteria. So one nice example people have found is so-called nitrogen vacancy center in diamond. It's basically a color center defect. It's a point defect in diamond, which is a wide gap semiconductor. So if you think about the diamond as a semiconductor, it has a very simple valence band structure and conduction band structure with a band gap of 5 electron volt. So this band gap is a special thing, and then in this band gap is sort of crystal vacuum because there is no energy state in this energy range. So if you think about this band gap as a crystal vacuum, then you can do interesting things, such as if you create defect. Now, defect is, for example, missing atom or foreign atoms replacing, the atom in the crystal. Then for some defects, you can create well-localized quantum states in this band gap. So now you can understand these states in the band gap as a sort of artificial atom trapped in the vacuum. Of course, now we are talking about crystal vacuum, but the physics is similar to the artificial atom as an artificial atom. So if you look at the diamond, it's sometimes it has colors like yellow colors or pinkish colors. These are all coming from the defect. But one of the color centers in diamond, which is now nitrogen vacancy center, is a special color centers because of its electronic structure. This electronic structure of the MB center, which is basically nitrogen impurity coupling with a vacancy. This is MB center. This MB center has a unique electronic structure which allows us to initialize this quantum state of the MB center using just optical light. So if you shine green laser on your MB center, it goes to interesting excited state dynamics, which is called intersystem crossing, which I'm not going to talk really details about it, but due to this electronic structure property, you can initialize your qubit using laser. And then using the same intersystem crossing property, you can also read out the spin state of the MB center using this by detecting this fluorescence coming from the diamond. And then this MB center has a ground state, which has a triplet spin state. Then you can use a conventional electron paramagnetic resonance technique to manipulate this spin state. And then amazingly, this is why this MV center becomes really popular. But amazingly, the MV center has a really long coherence time, which is about millisecond at the room temperature. So it is a quantum system operating at room temperature with a long coherence time. Okay. So there are other quantum system, solid state quantum system you can use as a qubit. So the other popular platform is so-called quantum dot. It's a self-assembled quantum dot. This is basically a semiconductor nanostructure, but I think I'm spending more time than I expected, so I can skip this part. But let me go to summary slide of this part. So other than the MV center in diamond, there are other sort of defect or impurity-based qubit system people are developing these days, such as the examples include donor spins in silicon. For example, you can dope your silicon with phosphorus, and this phosphorus has an electron spin. And then these days, people are just amazing. These days, people can pinpoint one donor spins and then do the quantum experiment. And these days, people are developing rare earth ion system, which is 4F electron system in complex oxide, and then transition metal ions in oxide and other semiconductors. Also, people are developing single photon emitters in two-dimensional materials. These are all sort of impurity-based single quantum system available in the solid state environment. These are sort of nice reference. So if you're interested in, I'm recommending you to go to the literature. Okay, so of course there are advantages and disadvantages. Yeah. I
have a question. Can you please go 2 slides back now already?
Sure.
Yes. No. The next slide, please. This was one too much. Yes, this one. So there are these. I'm looking at the top right picture of the levels and level structure, and there is this 2.87 gigahertz fine structure there. And what I was just wondering is whether this is not a problem at room temperature because of photon scattering, because in these systems, because this is a pretty small energy, right? And so photons, if I remember correctly, is tens of milli electron volts, and this is way less than that. So is there an issue with photons, or how, or why are they not important? Can you comment on that, please?
That's very excellent question, because that's where the magic kind of happens. Because as you pointed out, this energy scale 2.87 gigahertz, it's a micro electron volt, right? So which is called zero field splitting. It's a splitting in the spin sublevels due to the crystal field in the diamond. But then if you think about at room temperature, now because of this thermal energy, if you think about Boltzmann distribution, your system can occupy here and there and everywhere. It's everywhere.
Right.
So that's why we need initialization. Initialization means that it's a basic optical pumping. This intersystem crossing, what this intersystem crossing is doing is basically you excite system here in the upper branch, and then it goes to the excited state, and by doing this intersystem crossing, it's a pumping to this ground state. So if you keep shining your green laser light, your system is basically cooling down. It's basically cooling of your system to the ground state. Of course, there is a lifetime, which is spin relaxation time, which is called T1, due to the photon scattering, because if you wait long enough, your system will be thermalized. And then this time scale is a T1. And then T1 time is, I think, more than second. Because T1 relaxation time is determined by the spin orbit coupling and the photon scattering. And then the Debye temperature of diamond is really high, and the spin orbit coupling is small. So the photon scattering is relatively weak. And then T1 time is second, but we're talking about millisecond, the quantum coherence time, so we are fine.
Okay, thank you.
Good question. Yeah, so the advantage of using electron spins, we're talking about electron spins in the solid state, is that it has very large gyromagnetic ratio. So you can manipulate your spin using magnetic field very fast because the gyromagnetic ratio is coupling constant. So you can do unitary operation within few nanoseconds. So that's time scale of quantum control. And then it's in the solid state environment, so you can couple your qubit with the various degrees of freedom in the solid state. So you can it has more sort of opportunity to explore. And sometimes it has also nice spin photon interfaces. It has natural interfaces with photonic degrees of freedom. So using these spin photon interfaces, people are doing lots of interesting quantum experiments. And then there are, of course, challenges of developing solid state qubit, because we are mainly using impurity system or dopant. It's really hard to control the position and frequency of our quantum system, because solid state system is basically dirty system. So we have to sort of fight this the disorder or some inhomogeneous property of the solid state. Because of that, it's also hard to fabricate identical qubits, because sometimes if you're familiar with the solid state environment has inhomogeneous strains or sometimes inhomogeneous electric fields, things like that. Yeah. But most of research in this field is focused on kind of resolving these issues. Okay, so for application, let me just quickly go through the possible applications. So if you have coherent quantum system, then you can do lots of quantum information experiment, right? So a few years ago, now it's almost 7 years ago, excuse me. When this paper was published, lots of people were sort of surprised. So here in this experiment, they put 2 different diamond MV center in 2 different places, which are separated to each other by more than 1 kilometers. And then people have shown loophole-free Bell inequality violation using these 2 remote MV centers, using heralded entanglement generation schemes. And then these days, people are developing quantum computers using MV centers and nuclear spins in the nearby lattice. For example, in the diamond, you have carbon atoms, right? Diamond is carbon basically, but for some of the carbon atoms are 13 carbon isotopes, and they have nuclear spins. Then using MV centers, and then you can detect nearby nuclear spins, and then you can basically realize spin registers using these spins, and then you can also create this GHG state, and then measure the fidelity, and then do interesting quantum experiment. This is published last year. Also, another big sort of push in this literature is to use this coherent solid state quantum system as a quantum sensor, because it's a quantum system, and its phase is really sensitive to the external electric field or magnetic field. So, for example, you can attach your MV center in the cantilever type device, and then you can sort of map out the magnetic structure of your substrate. Or you can also use this MV center or other solid state qubit to measure or to detect or sense magnetic field, electric field, temperature, and other sort of external parameters at high sensitivity. All right, so far I've done I've talked about some basic ideas about using solid state impurity system as a qubit. And then the second part, I like to briefly talk about my own research work. So my own research work is, let me give you just basic idea. I'm working on materials, but I'm working on try to work on the coherent quantum systems embedded in the materials environment. In the materials environment, you first look at the periodic table, right? Dr. Arago warned me that before the talk, she warned me that for some of the audience may not be familiar with the periodic table. So, but I'm kind of sure that you're all familiar with the periodic table.
Well, I think this is impossible. I think this is impossible. We try to select only candidates who all know the periodic table.
Oh, okay. Good. So if you think about the MB Center that I introduced before, then it's basically defects in the diamond. But in more broad sense, it's an impurity system in wide gap semiconductor. But if you think about wide gap semiconductor, diamond is just only one example. In our nature, there are lots of different wide gap semiconductor. I mean semiconductor with a large band gap, and those materials also have lots of impurity system and color centers, right? Because nature is not perfect. Then people are developing, these days, like Bacon's defects in silicon carbide materials or 2D materials or nitride, oxide, all sorts of different wide gap semiconductors. Then my own research interest is this. Let me summarize as follows. So in our group, we try to understand this coherent defect-based quantum system in such heterogeneous and anisotropic materials environment. And the research question is that, can you actually engineer or use materials property to, for example, improve, let's say, coherence of your qubit system? Or can you find sort of decoherence protected subspace by engineering the materials property? So it's basically a combination, or I would say I'm trying to at the interface between material science and open quantum system. That's my kind of research position. So if you think in that way, there are lots of research opportunities that we can do, because materials is you have lots of degrees of freedom. Different materials have different chemical compositions or nuclear spin environment, or you can also go to reduce. These days, you can go to sort of reduce the dimensionality, and also there are surface issues and interface issues, and then probably you can ask how all these materials properties can affect the performance of your coherent qubit system, and vice versa. And this is very, I would think that this is important research kind of question, because it's an unexplored territory in the physical science history. So I see lots of interesting opportunities in this direction. So in our group, we approach this kind of research question in two different ways. The first one is we use electronic structure method, such as density functional theory or some other chemistry-based, wave function-based method to understand or to predict new type of defect qubits and new materials, or we try to understand how they kind of couple with solid state degrees of freedom, such as strain or electric field or phonons and photons. So we use mostly DFT and group theory and some other wave function based excited state theories. The second part Second method is that we use basically open quantum system approach. And then here we try to understand the spin dynamics or coherence dynamics of our qubit system embedded in the solid state environment. So we use basically effective spin Hamiltonian approach combined with density matrix method. And then we also try to combine these two methods together to find the new physics. Okay, so let me give you some, because here I put some references which has been published or which will be published in our group, by our group for each direction, but I cannot certainly talk all of them. But let me just pick one from here and one from there, and then giving you some basic idea. So for the first part, I like to talk about electronic structure method. And then here, it's a computational details. We use density functional theory, and then we also use so-called GW method, which is many-body perturbation theory, coupled with the conventional DFT method. And then the physical system that we are currently interested in is the single photon emitters in two-dimensional materials. It's basically defect system, but people found that it's a localized point defects in two-dimensional materials, such as hexagonal boron nitride. And then people found some of those defects emit single photons at room temperature. That's kind of driving force in this field. It's a single photon emitters working at room temperature. And then very recently, people have started to look at the spin properties of these defects. So if you have now spin degrees of freedom in this single photon emitter, it's basically MV center. It's basically like the MV center in diamond, and then it's a whole different story. So people are kind of excited about the development in this direction. But the main issue in this emerging sort of field is that, okay, you now in experiment you observe single photon emitters in two-dimensional materials, but those are defects. So the critical issue is that you don't know what they are, the atomic structure. You don't know the atomic structure of those defects, and then you have single photons coming from the two-dimensional materials, but the frequencies of those emitters are all different. It's inhomogeneous. Especially this inhomogeneous optical lines are sort of critical if you think about the quantum optics experiment, because the basic quantum optics experiment is that two-photon interference, right? If you want to do a two-photon interference, you have to have identical photons coming from two different spots. But in 2D material, you have single photons from different spots, but their optical properties are different. So it's a problem. To resolve this issue, people developed a way to apply strain to tune the optical lines, or you can also apply pressure, or you can apply ionic liquid, electrolytes to apply electric field. Then you can tune the optical lines, the single photons. So at the Aja University, this is sort of first project that I've done at my university, in collaboration with a Jin Lee group at the same university. So she did experiment and I did theoretical analysis. And then what we have done is that we've made the sandwich structure. We sandwich HBN material with a top graphene and bottom graphene. And what Jin Lee group has shown is that she applied the outer plane electric field across the sample. And then what she has observed is that actually you can tune the optical energy of single photons in HBN by applying the electric field. So this is basically Stark shift. But amazing thing is that, because the key thing of this experiment is that HBN is two-dimensional material. So it's a two-dimensional material stacked in this jet direction. And then she applied the electric field in this direction and show the stark shift. This is somewhat unexpected thing. That's why we kind of published this paper in this sort of good journal, Nano Letter. And then I kind of model this behavior using density functional theory. And then key sort of finding is that, let me just, because I'm running out of time. Key message is that I considered several possible defect models, which can be used as a defect candidate for single photon emitters in HBN. And then I found that this outer plane stark shift is basically related to symmetry breaking in the atomic structure of this defect models. So with this symmetry breaking or atomic tilt of this defect model, I was able to sort of reproduce this experimental stark shift as a function of outer plane electric field. This is kind of good example of how this material simulation can give you understanding on single quantum system embedded in the solid state environment. Okay, so next topic briefly is about quantum spin dynamics. So here we use basically density matrix formalism to understand the decoherence process occurring in the qubit system embedded in the solid state environment. So decoherence problem is a well-known problem in open quantum system literature. And in the solid state environment, the most important environmental degrees of freedom is basically paramagnetic centers. It could be nuclear spins or it could be electron spins. So, because usually we are looking at spin quantum bits in the solid state environment. If you have other paramagnetic centers nearby, then they can sort of create magnetic noise. That magnetic noise basically can destroy the quantum coherence of our qubit system. So now it's important to understand this decoherence dynamics. And once we understand the mechanism of this decoherence, then we can engineer our system to improve the coherence or enhance the coherence time. Just brief introduction of the decoherence is that decoherence is basically a time scale of the following process. For example, you start with the pure state. Your ensemble has all the pure state, such as superposition state shown here, up and down state. But if it's always interacting with the environment, right? Due to this environment, even though you start with the pure state, if you wait for long enough time, this pure state becomes classical mixed state. So quantum interference was there at the initial state, but after decoherence, it's not there anymore. So this is the process of decoherence. And the time scale of this process is called T2, which comes from the magnetic resonance literature. And then T2, it can be measured by this famous Hahn-echo pulse technique, which I'm not going to talk really in details. So there are two main approaches to understand this decoherence process. First one is top-down approach. I would say phenomenological models, and then one of the models is Lindeblad master equation. So this approach basically assumes that your environment is basically noise source. So you can always decouple your density matrix of combined system into your qubit density matrix and environmental density matrix all the time. And then you can model the noise effect as with this super operator approach. But the main issue of this top-down approach, of course, this is a good approach. You can understand a lot about lots of decoherence phenomena. But the important thing is that you don't know what is the exact noise kind of spectrum of your environmental degrees of freedom. So to resolve that issue, one can also do this bottom-up approach, which is microscopic calculation, and this is called quantum bath approach. In this approach, you basically solve the time evolution of the entire system, the combined system of qubit and environment using Schrödinger equation, which is and then after that you basically trace out your environmental degrees of freedom. Then this reduced density matrix has a coherence dynamics information. So and then this is what we are doing in our group, the microscopic calculation of coherence dynamics. I think I'm running out of time in maybe 4 minutes.
Oh, I think you're fine. So maybe 5 or even 10 minutes is okay.
Okay.
If you need more.
So let me give you some idea about this theoretical models by using the MB center in diamond as an example. So here I'm showing some schematic of MB center embedded in the oh, okay, I'm sorry, this is silicon carbide lattice. It's not diamond, but they're basically similar to each other. So for example, if you have spin qubits in the material, it's a defect center. Then in the nearby place area, you can have nuclear spins, for example, from different isotope. For carbon atoms, most of the carbon atoms, which is 12 carbon, doesn't have nuclear spin. But 13 carbon isotope has a nuclear spin. And the natural abundance of that 13 carbon is 1.1%. So if you have diamond like crystal, you always have nuclear spins in the lattice at 1.1%. And they're all distributed in the random places in the lattice site. Okay. Then we can set up our, and then this is environment. This is my sort of environmental degrees of freedom, the nuclear spins. So nuclear spins are everywhere. And then I have the MB center in the center. And then because of this nuclear spins are coupled to the MB center, whatever magnetic noise generated by the nuclear spin dynamics can destroy the MB center coherence. So this is what we are modeling. So because we need to calculate the time evolution of the density matrix, we need the Hamiltonian, of course. So the Hamiltonian comprises of basically spin the Hamiltonian for the MB center system Hamiltonian, and then nuclear spins are here. So this part is a Zeeman interaction of nuclear spins with the external magnetic field. But the important thing is that nuclear spins are magnetic dipole. So they are all interacting to each other by dipole-dipole coupling. So you have lots of nuclear spin and they're interacting to each other using by this dipole-dipole interaction. And then this nuclear spin bath is interacting with your spin through the hyperfine interaction. So in this sense, it's a basically strongly interacting system, strongly interacting many spin systems. In physics history, it's called the central spin model. And then what we do is that we calculate basically the time evolution of the whole, the density operator of the whole system. And then after that, we trace out the environmental degrees of freedom out, and we get the reduced density matrix. And we look at the off-diagonal element of this reduced density matrix, because that contains the coherence property of the MB center. of course, we cannot exactly diagonalize this matrix because typically, if you have one MB center in the center, it interacts with more than 1,000 nuclear spins. So the Hamiltonian has a dimension of the 2 to the 1,000, right? Which you cannot diagonalize it exactly. So what we are doing is called cluster correlation expansion. So the simplest approximation is that, of course, you ignore all the interaction between the nuclear spins, independent nuclear spin approximation. That's what we called a cluster correlation expansion 1. But that doesn't include the interaction between two nuclear spins, right? Then you can consider the pair dynamics of the nuclear spin, and this is called the CC2 approximation. Of course, there could be sort of multiple spin correlation terms, and then in this way, you can sort of increase this inclusion of correlation contribution system systematically. And then by doing this numerical simulation, we can calculate this coherence function of the MB center. And this is comparison between experiment and theory for it's not MB center in diamond, but it's similar system in different material, in silicon carbide. It's a silicon die vacancy spin qubit in silicon carbide, but they're mostly the same as MB center in diamond. So here I'm showing the experimental result on the coherence of this die vacancy qubit in silicon carbide as a function of magnetic field, and this is my theoretical result, which compare well with the experimental result. And then, or we can also compare, like, we can also overlap our theoretical result to the experiment and show excellent agreement with the experiment. And in this work, which was now published 4 years ago, we have calculated the coherence, decoherence time of this die vacancy qubit in silicon carbide as a function of magnetic field, and basically explain the experimentally measured the decoherence time of this qubit center. And then the very sort of the punchline of this work was that the decoherence time of this defect cubic center is actually longer than the diamond MB center, which was sort of amazing at that time. And then using this microscopic model, I explained basically the microscopic mechanism of this long coherence decoherence time. And then these days, recently we extend our method to understand the decoherence dynamics of spin qubits in two-dimensional materials and other complex oxide. And yes, so let me summarize my work, my talk using this slide. So we try to understand or predict the property of coherent quantum system, single quantum system embedded in the solid state environment, especially in wide gap semiconductors, in two different ways. First one, we use electronic structure method to understand basically coupling property of quantum states and materials degrees of freedom. And we also try to understand the decoherence or entanglement decay of our qubit system embedded in the solid state environment using open quantum system approach. Thank you for your attention, and I'm happy to take any questions.
Thank you for this wonderful talk. And yes, we are open for questions. So
yeah. Where did you get the sound?
It's on my mobile now. So Hosung, I have a few questions regarding the last part, because you say that your theory and experiment seem to give a very good agreement with respect to T2, but T2, this decoherence time from the block equations, it's a macroscopic time. So I mean, it's just a macroscopic parameter. When I look at your T2, basically. But if you go a few slides back, there's an experiment with all these, just maybe one more, yeah. So you can see these different peaks in the coherence. So on this slide, you can see these different peaks in the coherence.
Yeah.
And these, maybe they don't seem to match so well with the theory, right? So it seems that the macroscopic properties seem to be reproduced very well with your theory. But if I want to go into some details, would your theory be able to reproduce this as well?
You mean this peak?
Yes, for example, because I believe your theory does not have any any fitting parameters, right?
No fitting parameters.
Exactly.
Yeah. So I would say these kind of peaks are well reproduced in theory. This oscillation rapid, because there are two parts. It's a rapid oscillating part, and then envelope decay. So T2 means basically this envelope decay.
Exactly.
And then this sharp peaks or rapidly oscillating term is called electron spin echo envelope modulation, and this is due to the precession of nuclear spin. Yeah, and which is reproduced well in my theory as well. So I was able to actually compare this rapid oscillation of coherence with my theory, and then it's
what
not
are the peak
exactly
heights corresponding to? Right, and what are the peak heights corresponding to? So the peak heights, but that seems to be a bit off, if I'm not mistaken, or maybe
yeah, a little bit off, but trend is there. You can see the overall trend is there.
Okay. Other questions from the audience?
I have a question.
Yeah, please go ahead.
Yeah, thank you for your very nice talk.
Thank you.
Could you? I have two questions actually. Could you explain? The first one is the first part in your result, HBN and carbon impurity. So could you explain why do you think the carbon impurity is most likely the impurity that can be single photon emitter?
Oh, okay. Oh, that's a very good question. We don't know.
Yeah. So yeah, but my question is that
that's why I kind of consider different impurity models here. But they all show the same trend.
I see.
Yeah.
So
yeah, the thing you basically touched on the main issue in this literature. In sort of theoretical kind of literature, we know what's inside the material because that's what we model, right? We can put carbon atom, oxygen atoms, and we can model those in specific impurities, but we don't know if they really exist in real materials. In real materials, they observe single photon emitters, but they don't know what they are because we try to meet each other at the sort of intersection, experiment and theory, by analyzing different spectroscopic sort of data, things like that. Yeah, that's a very good question.
Yeah, thank you. And other question is that in your second part, you assume that the decoherence, the reason that make such a decoherence is mainly nuclear spin, interaction with nuclear spin and NV center electron spin.
Yeah.
Then, but I know there are other factors that can induce some decoherence, like for example, electron phonon interaction.
Yeah.
I was wondering. Yeah, I was wondering. Which one is much more significant in making some decoherence? Do you think nuclear spin is much more severe than electron phonon?
Yeah, that's another very good point. And it depends, as always. It depends. In this sample, we have tested lots of scenario, and then in this sample, experimental sample, it seems that nuclear spin is the dominant source. But if you increase the temperature of the sample, now this electron phonon coupling start to come into play, because they start to limit the coherence time. And then in this sample, we don't have much electron spins nearby due to the other paramagnetic defect. But if your sample is sort of dirty enough, you have lots of dislocations or vacancies or dangling bonds, things like that. Then you have lots of electron spins in a bath, and that electron spins basically dominate the decoherence problem. But in this sample, the sample was clean. There are no sort of negligible amount of electron spins, paramagnetic defects, and then we cool down the sample to sufficiently low temperature to kind of remove the electron phonon effect. Then the leftover is the nuclear spins, which is intrinsic factors in the materials. Yeah.
So do you mean that in the low temperature limit, electron phonon will not affect a lot?
Yes, because electron phonon interaction give you T1 relaxation time. Yeah. T1 is your spin is flipped, your population changes. That basically give you the fundamental limit to the T2, the coherence time. So fundamentally, T2 is limited by 2T1, 2 times T1. But at low temperature, T1 becomes really long. It's more than like more than second. Like sometimes it goes to minutes. But we're in T2 time scale is basically millisecond. So it doesn't limit the coherence time.
Thank you.
Yeah.
Okay, we have another question from Jung Yun. Please go ahead.
Hi, Professor, sir. Thank you for your last talk. And I have a very basic question on deuterium vacancy centers.
Yeah.
So first of all, what system did you refer? Is it vacancy or the electron in the center?
Nitrogen vacancy is a defect complex. It's a combination of nitrogen impurity with a vacancy.
Yeah, then the system what you refer is the defect?
Yeah, it's a defect.
Is it correct?
Yeah.
I see. Then the next question is because we usually consider some weak interaction between system and bus to describe the microscopic theory in order to drive the Lindenberg equation somehow.
Yeah.
So
that's right.
I wonder, is the energy scale between, the interaction between defect and environment, is it much smaller compared to any other system parameters of the, let's say, energy of defect or energy of environment? Is it guaranteed?
That's a very good question. First of all, we are not using the Lindenblad equation, so we're free from the assumptions made there. Mm-hmm. We're using fully quantum mechanical calculation. It's not semi-classical calculation. But again, but your second comment is fair, because we are using cluster expansion calculation, which also assume that the system environment coupling is weaker.
Yes.
But that approximation is valid in our model, because here we are talking about electron spin as a qubit and the nuclear spin as our path. In the electron spin, you have this Giemann interaction, which is order of gigahertz. But the electron spin interaction with the nuclear spin is mediated by the hyperfine interaction, which is basically dipole-dipole interaction. And then this coupling constant is about kilohertz or less than megahertz, because it is proportional to the gamma E times gamma N. So it's 1,000 times smaller than the gamma E. Yeah, so we can use a secular approximation and then central spin approximation. That's very good question.
I see. I have a last question, because MV center is well known to exhibit very long coherence time compared to the, any other qubit systems. Can you explain briefly why this system can exhibit long coherence time compared to any optical system, let's say?
What do you mean by optical system?
Just compared to the optical qubit setup, because this MV center shows very long coherence time. So
yeah, there are two reasons, basically basic reasons, because here I've calculate the coherence time of the MV center as well. Yeah, so this is MV coherence time as a function of magnetic field. And the theoretical limit of MV coherence time, T2 Hahn-echo coherence time, is 0.8 millisecond. And experimentally, it's known, it has been measured to be like 0.7 millisecond. But that long coherence time is due to basically two things. First, in this sample, the dominant decoherence source is nuclear spin again. But there are only 1.1% nuclear spins in the lattice, which is low. So there are not many like paramagnetic spins nearby. That's one thing. And then you can also dilute, you can make more dilute nuclear spin bed by doing this isotopic purification. Then your coherence time becomes longer and longer, even longer. The second reason is that this the MV center's electronic orbitals, they are well separated from the bulk state, bulk diamond state. They are trapped in the band gap of the diamond. So it's a sort of artificial atoms trapped in vacuum, in crystal vacuum. So it's a sort of protected from the outside world by like electric field or other sort of perturbation. And then MV center decoherence is also known to be robust as a function of temperature. If you increase the temperature, you can measure the MV coherence at room temperature, and it's still close to the millisecond. This is because the diamond Dubai temperature is very high, so you have very low density of acoustic phonons, and then spin orbit coupling is small. So your spin is not sort of affected by the phonon degrees of freedom at high temperature. That's basically basic reason why MV center has a long coherence time at room temperature.
I see. Yeah. Thank you very much. Yep.
Thank you.
Okay. More questions from the audience? So it doesn't seem like. So if not, let us please thank our speaker once again.
Thank you.
Great. So I think we end our official PCS seminar here, and now we continue towards a discussion session. So thank you all for joining in.
Thank you.